Hello everyone, in today's video we want to talk about directional derivative optimization. Now what we noticed from the directional derivative is that if I have, well, I guess the best example is to do like some sort of elliptic paraboloid or something like that, or the case where we have a circular paraboloid. I want to find the directional derivative at this point, say, maybe. So this gives me some sort of surface here for finding it along this side, right? Then I could also find it along this side. Maybe I'd get a different surface, and that might have a different slope, right? So one of the problems, right, for the directional derivative is we're given so many options for which direction to take our slope across the function that we don't really know what to do with it. So what we want to do today is determine how do we find the maximum rate of increase. So what is the maximum rate of any directional derivative at our point? So I want to find the highest rate of increase. So that's what we're going to do today. The derivation for this is actually fairly simple. So what we do is we take the definition that we've made for the directional derivative in the direction of u hat of a function f equals nabla f dotted with u hat. So note that both of these are vectors. Well, we can rewrite this now in terms of magnitudes and the angle between them. If we know the angle of nabla f and we know the angle of u hat, or the angle between nabla f and u hat, we can use an alternative definition for the dot product. So this could be equal to the magnitude of nabla f times the magnitude of u hat times the cosine of theta, right? So now what we do is we recognize that the magnitude of a unit vector is by definition 1, so this is equal to the magnitude of nabla f times cosine of theta. However, we also know that the maximum of the cosine of theta is equal to 1. So if we want to make this the maximum, then theta will equal 1. Or theta will equal 0. Theta won't equal 1. Theta will be 0. So what does this mean? This means that the maximum of the directional derivative of f is just equal to nabla f, because this cosine of theta becomes 1, so we just get magnitude of nabla f. So this means that the maximum of our directional derivative is when our unit vector is in the same direction as the gradient, okay? So the gradient will give us the maximum directional derivative, or the gradient will give us the direction that we should use for the directional derivative. Let's try an example here. So let's consider that the temperature at any given point, x, y, z, is modeled by the function 80 over 1 plus x squared plus 2y squared plus 3z squared. And I want us to find the maximum increase rate at the point 1, 1, negative 2. Okay? So first what we want to find is we want to find the gradient of our temperature function. So to do that, we take partial derivatives with respect to both x, y, and z. And then this requires a chain rule or substitution, if you will, for each partial derivative. We get for the first component negative 160x over 1 plus x squared plus 2y squared plus 3z squared squared. And then for the y component, we get negative 320y over 1 plus x squared plus 320, or plus 2y squared plus 3z squared squared. And then finally, for the z component, we get negative 480z over 1 plus x squared plus 2y squared plus 3z squared squared. We can take out a factor of 160 over 1 plus x squared plus 2y squared plus 3z squared squared, and then we're left with a vector negative x, negative 2y, negative 3z. So now what we want to do is we want to find the magnitude of our gradient vector at the point. We want to find the magnitude of the gradient vector at our point 1, 1, 2, negative 2. So we find the gradient vector, which is 5/8, negative 1, negative 2, 6. And we find the magnitude of that, and then we just sum all of the squares of the components. We multiply it by whatever constant we've got out there. So we get 5/8 times the square root of 41, right? So what this means is maybe you could envision, it's very hard to envision three-dimensional functions or three-dimensional inputs and a fourth-dimensional output. So the way that you could maybe think about that is, say I have a point here. Each point is assigned to a color, and the color is kind of your output. So maybe red would be some really low number, purple would be some very high number, right? So you can think about maximum rates of increase. Well, it's very hard to interpret these higher dimensional functions, obviously, because we live in three-dimensional space. But you can use tricks such as color to help you out there. All right, thanks for watching. In the next video, I would like to talk about tangent planes and level surfaces a little bit more in the context of the gradient. And then I'd like to start talking about optimization. So we'll do that then. See you there.